And now I think it's time for the next talk. Daniel Spiegel will continue with his series of talks and will continue with dynamics in the C-star algebraic setting. Thank you.
Right, thank you, Marcus. Right, so we were talking about derivations, and it's time now to relate these to ground states. So we had this definition of ground states in terms of the GNS Hamiltonian, and I'm going to show you that this derivation is a more direct object for getting at the ground state. OK, but I want to recognize that this derivation and this Hamiltonian are very similar objects. They're sort of two sides of the same coin. Namely, they're both derivatives of one-parameter groups of isometries on a Banach space. So that Banach space can be a Hilbert space, or it can be a C-star algebra. And you could have a family of unitaries or a family of automorphisms. But either way, we're dealing with a family of isometries on a Banach space. So it pays to take a step back and study it in that more abstract sense. OK, so let me set up some notation that I'm going to use throughout the lecture. And I'm sure I'll mix up a symbol at some point. And if I do, just yell at me. OK, so x here, curly x, is going to be a Banach space. Eta is going to be a one-parameter group of isometries, strongly continuous. And I'll define Xi to be its generator. So this is defined on some dense, or on some linear subspace. And it takes values in x, and it's the derivative. As we had before, it's the derivative of the family of isometries at s equals 0. Derivative at s equals 0. OK, so we're going to study this thing in the abstract for an arbitrary Banach space. But I also am going to flip back to the C-star algebraic point of view every now and then. So I'm also going to have a C-star algebra as before. And we'll have our same notation. So we'll have tau t delta as before. And I'll fix a state omega in the state space of the C-star algebra. OK, with GNS representation. H by omega. Sorry, let me write that better. What? There's no Hilbert space here at all. I haven't assumed that there's any Hilbert space, so there's no. Well, I mean, there's the Hilbert space structure, but it's sort of right here. The representation is, I sort of started with this state, and I constructed this Hilbert space by defining some inner product in terms of the state. I don't think you would get anything else by trying to pull back. OK. So right, I'll stick to this notation. This will just help me not repeat myself a million times when I write a theorem. OK. So we saw in Bob's talk that it was useful to integrate this automorphism group against some weight. And that's a useful idea in this context as well, in generality. And the weight I'm going to use is an exponential. So we're going to do a Laplace transform. So I'm going to define an operator for lambda greater than 0. We're going to have r lambda of x. So r lambda is a function from the Banach space to itself. And r lambda of x is going to be a Laplace transform. So it's integral from 0 to infinity minus lambda s with respect to eta s. of x ds. OK. This is called a resolvent, and you'll see why in a second. This is a very useful tool because it plays very nicely with the generator, xi. So some properties. R lambda, first of all, it commutes with the automorphism group, or the isometry group. And then the reason it's called a resolvent is because it's an inverse for lambda minus xi. So if x is in the domain of xi, then R lambda of lambda minus xi of x is x. And it turns out this is a two-sided inverse. So for any x in the Banach space, actually R lambda of x has its image in the domain of xi. So it makes sense to reverse these operators. And I still get the identity. And the final property which I want to mention, which will have a very nice corollary, is that the limit as lambda goes to infinity of lambda R lambda of x is equal to x for all x in the Banach space. OK, these are very simple properties to check. Yeah, question? Well, I just meant that this expression makes sense. You have to check here that R lambda of x is differentiable, meaning that it's in the domain of xi. That this thing, when I apply the isometry group, it's differentiable. So it's in the domain of xi. So this expression makes sense. If it wasn't in the domain of psi, I couldn't apply xi. That's all I meant. Another question?
Just out of curiosity, so like if my Banach space is
I have no idea. I mean, OK, this is not within my knowledge. Sorry. OK. So this property has a very nice corollary, which is very easy to see. And this shows us that the domain of xi is dense in the Banach space. Right? Because all of these elements are in the domain, and they approximate an arbitrary element of the Banach space. So this is very useful. It would have been very bad, again, if this domain of xi was empty or very small. Before we showed it was dense for the particular example. Now we have that it's dense in general. Okay? And with this density, I can now characterize invariant states. So let's go back to the C-star algebraic framework. The state, so the following are equivalent. Omega is invariant. Omega of delta of A. Remember, delta is like my psi, just in a different context. This is equal to 0 for all A in the domain of delta. And another way I could write this is I omega of A star delta of A is equal to 0, or sorry, is in the real numbers for all A in the domain of delta. And that last one will become useful in a little bit, just in a second. But let me write these, we'll call this A, B, and C. OK, so we can do the proof. Proof is now very simple. So A implies B. Well, we'll just take a derivative. Right, so omega of delta of A is by definition equal to the derivative at time t equals 0 of omega of alpha t, or sorry, not alpha, tau, at t equals 0. But I know that this is invariant by assumption. So this is the derivative of omega A at t equals 0, but omega A is a constant. OK, very good. Let's see, B implies C. Yeah, Daniel.
Why? It seems like we interchange the omega and the derivative.
Yeah, that's OK. Omega is a continuous linear function. So yeah, there's no problem there. But thank you for asking. OK, so we want to show that this quantity now is in the real numbers. So let's take its complex conjugate and show that we get the same thing. OK? So the complex conjugate how many parentheses do I need? There. OK, that reverses the I. Complex conjugates can be pulled inside of states. So I'm going to do that. I'm going to get a star operation on the thing inside. That's going to be delta of A star A. And now I use the product rule for the derivation. This is minus I omega delta of A star A minus delta minus A star delta of A. This first term is 0 by hypothesis. And so I get I omega of A star delta of A, which is what I started with. So I took the complex conjugate, and I got the same thing back. OK, now we just have to do C implies A. Oh, I wasn't supposed to erase my notation. Oh, OK. I'll leave it up. What's left of it? OK, so C implies A. Right, we want to show that it's invariant. So let's use the fact that this is a real number. So like before, we know that the complex conjugate of this is itself. And the complex conjugate is delta of A star A. And so if I just move this to the other side and use the product rule, I get I omega of delta of A star A is equal to 0. This is for all A in the domain of delta. And now by the same argument I used here, this implies, well, let's look at omega of alpha t of A star A and take a derivative. We'll show it's constant. The derivative of this is omega of delta of alpha t A star A. I'm not evaluating the derivative at t equals 0. That's why there's an alpha t here. This is omega of delta of A t. See, this is what happens when you switch notation too much. And tau t of A is in the domain of delta. So this is 0. So I have now that omega of tau t of A star A is equal, it's constant, and therefore equal to its value at t equals 0, which is just omega of A star A. This was for all A in the domain of delta. But now we know the domain of delta is dense. And therefore, we know that this is true for all A in the C-star algebra. And then there's a fact which that any element of a C-star algebra can be written as a linear combination of 4 positive elements. So the fact that this is invariant on positive elements implies that it's invariant on all elements. OK. So this was by density. And then this implies omega of tau t of A equals omega of A for all A and A. OK. So good. Yeah. That was this assumption. So I assumed B, and I used it there. Right, but the domain of delta is a star algebra. Yeah. OK. You could do that for a self-adjoint A. In general, so let me write it where I erased my notation. A in A can be written as A equals B star B minus C star C plus I D star D minus E star E, like that. All right, so that's invariant states. We now have a very nice description in terms of delta, which is a very concrete object itself. Let's talk about ground states. And if we're going to talk about ground states, we're going to need to relate delta to the GNS Hamiltonian. And that, fortunately, is very easy to do. So if A is in the domain of delta, then pi A omega is in the domain of H. So I forgot to say, if omega is invariant. Right, I always need an invariant state in order to even define the GNS Hamiltonian. OK, then pi A omega is in the domain of H. And IH pi A omega, I can evaluate this explicitly. It's pi of delta of A omega. OK, so proof is extremely simple. By definition, IH omega is the derivative of UT pi A omega evaluated at t equals 0. And now I use the property of this ut. It commutes with this pi and introduces a tau t. So this is d by dt pi of tau t of A ut omega. Ut omega, or omega is invariant. So this is d by dt by tau t of A omega. And this is differentiable by assumption with derivative delta. So that's a very nice little calculation. OK, and now I can talk about ground states. I'm going to go up because I want to leave this here for 1 second. Okay. I can now give a description of ground states in terms of delta. And I can also call this A. And the equivalent condition is that we have the following inequality. Okay, so right, this looks a little funny, this looks a little funny. What does this mean? So you should think of this delta as like a commutator with h, morally. And so this condition is sort of saying that omega of a star HA is greater than 0. And so let me write this out. This is omega HA minus a star AH. I want this to be greater than 0. This H acts on a GNS vector on the right, and it kills it. So this being positive is saying, like, for any local operator, I can only increase the energy of the state. That's what this being 0 means, or greater than or equal to 0 means. I act with a local operator, and I increase the expectation value of h from 0. OK. So let's prove this. If omega is a ground state, it's by assumption invariant. OK, so there's a GNS Hamiltonian. And we can just compute this quantity here. So this is a star delta of A. This is, we descend to the GNS representation, pi of a star delta of A omega. We can pull this pi of a star to the other side. And this pi of delta of A becomes an IH. And the i's kill each other. And I get a h pi a omega. And this is greater than or equal to 0 because by assumption, h is positive. OK? Let's do the other direction. So by this theorem, if minus I omega of a star delta A is greater than or equal to 0, it's in particular real. So by this theorem, I know omega is invariant. Okay? And I still have this calculation. That still works. And by assumption, this is greater than or equal to 0. So everything in this line is still true. And therefore, since pi of d delta omega is dense in H, we know that psi H psi is greater than or equal to 0 for all psi in the domain of H by a density and continuity argument. Yes, Robert. What's your question? How does pi of delta of A become h of pi of A? That's right here, right? This. Yes, Daniel. Maybe you'll ask the question I wanted you to ask. Or one, Robert.
Continuity argument when H is unbounded.
Thank you. Yes, so this doesn't work. You're a very good audience member. So no, this doesn't work. H is not continuous, so we cannot apply this argument. OK, what's needed to complete the proof here is the notion of a core. A core is a subspace of the domain of this generator that allows me to apply these kinds of density and continuity arguments. So let me define it for you. And we'll define it in this abstract Banach space sense, OK? So let's say let T be an operator on X. D of T here is the domain of T. It's a subspace of X. Let T be linear. And we say a subspace of the domain, D naught, is a core for T if for every x in the domain of T, there exists a sequence in the core such that it looks like T is acting continuously. So not only xn goes to x, but txn goes to tx. OK, so another way of saying this is that the graph of T on D naught is dense in the graph of T. OK, so this is the kind of thing we need. We need to identify a core for this GNS Hamiltonian in order to complete this argument. And we have some very general theory for identifying cores for these generators. So our first theorem for identifying a core is if D naught is dense in the domain of Xi, and it's invariant under the group of isometries, then that's all I need. Then D naught is a core. OK? And this has the corollary in the C-star algebraic context that pi of d delta of omega is a core for H, assuming omega is invariant, of course. And let's prove that. We just need to see that this thing is invariant. We already know it's dense. And to see that it's invariant is very simple. Take A in the domain of delta. We now want to know, we want to know that it's invariant under ut. This a to t, I'm trying to find a core for H, so I'm thinking of ut as my family of isometries. Okay, so ut pi a omega, by definition of these uts, is pi tau t a omega, and this is in pi of the domain of delta applied to omega, just because tau t leaves the domain of delta invariant. OK, with that, I can finish this argument properly, and I can conclude now that this theorem is true. Yeah? It's guaranteed. I didn't say that, but it's guaranteed to be. Oh, right here, you mean? No, I didn't require that. I mean, but the generators that we're working with they're closed. So, yeah. And you can see that from the resolvent, by the way. It's an easy calculation. OK, good. And let me add to this theorem, now that we know about cores, we could only check this it would be sufficient to only check this on a core for delta. Right now we only have a core for the GNS Hamiltonian, but if we had a core for delta, it would be sufficient to check on the core. So sort of ran out of room. Let me say for all A in a core of delta. That would also be sufficient. So we have another general theorem. And I want you to remember now that bounded finite range interaction we had, that we had a convergent Taylor series. And in general, we say x in the domain of this generator is analytic for the generator if this sum, the Taylor series, converges for some positive, write the generator here, for some positive time. OK, so that's what we had before, right? We had the generator delta for the bounded finite range interaction. It had this convergent Taylor series on the local algebra. So then the theorem is that if delta naught is dense in D of the generator, the domain of the generator, it consists of analytic elements, for xi, and xi leaves this D naught invariant, well, then that's enough to give me a core. Oh, thank you. Yes. Yeah. Right, then D naught is a core. OK, I won't prove that right now. But this is all I need to conclude that A loc is a core for a bounded finite range interaction. So if delta comes from a bounded finite range interaction, then the local algebra is a core. And so it suffices just to check this inequality, minus I omega of A star delta of A greater than or equals to 0 on the local algebra. And that's very nice, because if we didn't know a core for delta, we'd still sort of be in this difficult to check land, because I'd have to have some handle on what A in the domain is. But I have a very good handle on what a local operator is, and so it's easy to check that condition now. And if you come to the problem session, there will be an example for you to compute. OK. Yes, I'll erase this. I want to keep talking about properties of ground states. And I want to give you one more equivalent definition of a ground state, which is not necessarily supposed to be easy to check, but is going to give us a very important corollary. So earlier we did the Laplace transform of the family of isometries. This worked out really well for us. We can think about integrating against any L1 function. So what do I want to say? Given f in L1 of R, we can define, I'll call it tau f. Tau f of A is going to be the integral with f as my weight. OK? So now tau f is a bounded linear function. On my C-star algebra. And the equivalent condition is the following. So omega is a ground state. If and only if omega applied to this tau f of A star, tau f of A, is equal to 0 for all f in L1 such that the Fourier transform is 0 for all negative values, or non-positive values. So this is an equivalent condition. And maybe if I have time, I'll do one direction. But let me just say what its consequence is. So the corollary of this is that the set of ground states is a face of the state space. So the state space is convex, and the extreme points are the pure states. And a face, so a face of a convex set C is a subset, a convex subset. Call it F subset of C, such that if X is in F, let me write it here. So X in F, T in 0, 1, and X1, X2 in C, such that X is this non-trivial non-trivial convex combination of x1 and x2, this implies that x1 and x2 are in F. So for an extreme point, it implied that x1 and x2 were equal to x. For a face, it implies that they're just in the face. So then the corollary is that the set of ground states of tau is a face of S of A, of the state space, the whole state space. Because if you tried to write a ground state in terms of two other states, the fact that the ground state was equal to 0 on all elements of this form would imply that the two other states had to be equal to 0 on all elements of this form, because they would have to be positive. States map positive elements to positive numbers. So this would force this omega 1 and omega 2 to be states, yeah, or ground states. Yes, thank you. And in particular, extreme points of a face are extreme points of the whole set. So if I have an extreme point of F, it's also an extreme point of C. And so a very nice corollary is that if there's only one ground state, if tau has a unique ground state, then it is automatically an extreme point, and therefore it's pure. OK. OK, I have 10 minutes. So let me do one direction of this theorem. But it will be a little technical. I think I can erase this now. So let's assume we have a ground state. And let's try and evaluate this thing. OK. Good. So this is omega of tau f of a star, tau f of a. In the GNS representation, that looks like omega pi. Well, it looks like pi tau f of a omega pi tau f of a omega. Let me expand out one of these. So this is the integral of r f of s. And then I have pi tau f of a omega. And then I have a tau s of a that gets trapped in there. And this tau s of a I can now rewrite in terms of the unitary, u of s, or us. So this is fs pi tau f of a applied to omega. And then I get us pi of a omega. And us is the exponential of, it's e to the I s h. So this is f of s. And then I can write it like this. I can write e to the I s lambda. I'll have dE. E here is going to be the spectral measure associated to the Hamiltonian. And I apologize if you haven't seen that before. But a physicist might write it like, so I'm going to write, physicists might write something like dE lambda as d lambda lambda, or something like that, where these lambdas are the eigenvalues of, or eigenvectors of, maybe I should write like psi lambda, psi lambda. OK? So these psi lambdas would be like the lambda eigenvectors of H. So this is then pi tau f a omega pi a omega. This is a complex measure that I get by sandwiching this on both sides with my actual vectors here. So this is as a lambda, and this is ds. Let me continue over here. I'm going to use Fubini's theorem now. I get integral. Oh, there's another integral with respect to this projection valued measure. I use Fubini's theorem to switch the order of integration. I'm integrating the projection valued measure over the spectrum of H. And I have an integral here f of s e to the I s lambda ds d e. OK, and this was the Fourier transform. Or at least it's the Fourier transform on minus lambda. Let me drop all the subscripts. And this was assumed to be 0. If h is, or if omega is a ground state, this h is a positive operator. All these lambdas are positive numbers. And I assumed that the Fourier transform was 0 for negative numbers. So that's one direction. And I think I'm a little bit early, but I certainly cannot do the other direction in 4 minutes, although it's similar. But one needs to make more careful arguments. So I'll stop there. I thank you for your attention. See you at the problem session.
Are there questions? OK.
Maybe this is on a slight tangent, but is there a connection between the spectral measure and the density of states of such a system?
I don't know.
OK.
I don't usually think in those terms. But yeah. Maybe Simon has an answer, and maybe. Oh, question. OK.
So this tau f obviously looks like what Sven has mentioned, and Caroline has mentioned, the adiabatic, quasi-adiabatic generator, right?
Well, I didn't take it. I mean, I wouldn't say quite like that, right? There's no derivatives of the Hamiltonian in here, so I'm not so sure. But I guess it's similar. I'm integrating.
If we
Similar. Yeah. OK.
It's one.
One example. Oh, OK.
Yeah. And if we choose A to be just the Hamiltonian, isn't it the Q quasi-adiabatic generator? OK.
Okay.
Yeah.
Yes.
OK. Thank you.
OK. Thank you. Sorry.
OK. So let's thank the speaker again.